Okay, so let us start with this topic, uh, Darlington emitter follower. Okay, so before this we had seen uh, a basic DC amplifier. Okay, that consisted of a simple two stage. Okay, this was the first stage. Okay, and this was the second stage. We saw this thing, and we observed that with each stage the battery strength should increase. Okay, so it means that VBB3 was should be higher than VBB2, and VBB2 should be higher than VBB1. Okay, and this is applicable with each stage. So it means that with each stage we need a stronger battery, and this puts a limitation on the number of stages that we can cascade, that we can use. Because we cannot increase the strength of battery as we want. Okay, we cannot go above a certain value. Okay, this is electronic circuits, so maximum we can go up to 25-30 volts. We cannot go above that. Okay, so there is a limitation, and these batteries require maintenance, and we also know that these batteries have shunt capacitance. Okay, and these capacitances deteriorates the performance of the amplifier at higher frequencies. Okay, but the question is how these batteries have got shunt capacitance. Remember, these are batteries, and we if you remember the rectifier circuit, rectifier means the circuit which converted AC into DC. Okay, so during the conversion from AC into DC, okay, there is use of those filter circuits in between, and filter circuit consists of these capacitors. Okay, and so there is inherent use of capacitance in the circuit which is used to convert AC into DC. Okay, and because of those capacitances, the effect of those are visible on the performance of the amplifier. Okay, so remember, wherever you find a capacitance or inductor, okay, and knowing that the capacitors and inductors are reactive elements, so their performance changes with respect to frequency. This is one thing, and this is the basic thing. So wherever there is a capacitance, its behavior will change with respect to frequency. Okay, and that is why this statement is here. This point is here. Okay. So now starting with the Darlington emitter follower again, you might be aware of this. This this is a pair. So this consists of two transistors. They are connected back to back. Okay. So look at here. This is the first transistor Q1, and uh, and this is the second transistor Q2. Okay, and Q1 and Q2 are connected back to back. Okay, the input is provided at the base of Q1. Okay, and this is the emitter terminal, and this is the collector terminal. Okay, the characteristics of this Darlington emitter follower or Darlington pair is that it has got a very high current gain. Okay, and we will take the output across the emitter terminal of Q2. From here the output terminal will be taken out. Okay, and the current in this branch will be the current, that is the emitter current of Q2. Okay, and we know that the value of Q emitter current is high, very high, as compared to the value of this base current. Okay, and this base current is actually coming from this emitter current, and this itself is very high as compared to this base current. So as a result, the output current across this emitter in this emitter branch will be very high as compared to the base current of this terminal, input terminal. Okay, so that is why it has got a very high current gain, and it has also got a very high input impedance. Okay, because the output is taken across the emitter terminal here. Okay, and so it means that in that sense it is a common collector amplifier. So the collector terminal is common between the output and the input, those things. Okay, and this is the base collector junction. Okay, and this is the base emitter junction, right? And if you look from the input side, okay, we know that the base emitter junction should be forward biased and base collector junction should be reverse biased. Okay, and uh, from the input side, this will look, when you look, this will come into the picture, and the resistance of this particular junction, which is reverse biased, okay, will be the overall resistance of the whole pair. Okay, and since this is reverse biased, and reverse biased junction has got a very high impedance, very high resistance, we know this thing. Okay, and so it has got a very high input impedance, right? And these things, this pair is very common, very popular. Okay, and these are made available in a single package to be used in the circuits. Okay, and these are very simple and convenient to use. Okay, because look at this circuit. What is this? A very simple straightforward circuit, right? Okay, sorry. And the same emitter Darlington pair being used here, and mm, this is the input signal that is provided at the input side. Okay, the Vs, the source voltage source, input voltage source, and the output voltage is taken across this Re. Remember, one Re resistance is inserted at the emitter terminal of Q2. Okay. Okay, just a second. Take some water. Okay, and this Rs is the source resistance of this particular source. Okay, we know that every source has got its some internal resistance or internal impedance. So this is the internal impedance, internal resistance of this particular source, and this is a voltage source. So this is represented in series with Vs. Okay, so some voltage drop will occur across this, and the remaining voltage will appear across these terminals. Let us take this as the input voltage that appears across this circuit. Okay, and this V naught is taken across this Re, and this is our output voltage. Okay, and one very important point regarding Re, because we know that this Re has got a very special role here in the circuit. Okay, we know that whenever we insert a resistor in the emitter branch, it stabilizes the circuit. It makes the circuit more stable. Okay, so the purpose of this resistance Re, whenever you see this in the emitter branch, you understand that that particular circuit is a stable one. Okay, and why this makes the circuit more stable is because the insertion of Re here gives us the benefit of using negative feedback. Okay, and we know that negative feedback is something that makes the circuit more stable. Okay, so the insertion of this Re here gives us the benefit of using negative feedback in the circuit, and because of that the circuit becomes more stable as compared to with respect to the changes in the voltage or temperature or beta. Okay, that is the thing. Okay, that is why this you will see almost Re everywhere in the circuits. Okay, so across Re we are taking the output, and this is the output voltage V naught that is coming here. Okay, and this is the plus VCC voltage that is applied at the collector of Q1 and Q2. This is used for the biasing purpose, right? So next is let us go through this hybrid parameters, because in this book they have analyzed the circuit. They have given the parameters, the four important parameters. The four important parameters, those are the input impedance, output impedance, the voltage gain, and the current gain. Okay, so these are the four parameters that are particularly important from an amplifier point of view. Okay, any amplifier can be wherever you see, you will see the analysis in terms of these four parameters. And what are these parameters? The input and output impedance, the voltage gain, and the current gain. Okay, and in this book they have given these parameters in terms of they have analyzed these using this hybrid parameter modeling. Okay, and remember again that there are two types of modeling. We can model the BJT based circuits, we can model the BJT based on hybrid parameter models, or there's another called as RE model that can also be used for modeling the BJT circuits. Okay, and they are if you know one set of modeling, then you can easily convert those parameters into another set of modelings. Okay, so there is a possible conversion between hybrid parameters and RE model parameters. Okay, and vice versa. So they are like interchangeable in the sense they are related with each other. Okay, and if you know that relation, you can change from one modeling style to another modeling style. Okay, so this is the thing. So let us go with these hybrid parameters. And the hybrid parameter equations are described by this, where v1 is equal to h11 I1 plus h12 v2, sorry. Okay, and I2 is equal to h21 I1. Okay, this should be I1 here. uh, I1 plus h22 v2, h22 v2. Okay, where v1 and I1 are the input voltage and currents, and v2 and I2 are the output voltage and currents. Okay, so v1 is input, I1 is input current, v2 is output voltage, and I2 is output current. Okay, now this is v1, left hand side is v1, that is a voltage. Okay, so it means that the right hand side should also be a voltage. Okay, thing, or these terms should have a unit of voltage, that is volts. Okay, and this term should also be having a unit of volts. Okay, so from here we can determine the unit of h11 h12. Look at here, v2 into h12, so v2 is itself a voltage. So it indicates that the unit of h12 would be nothing. So h12 is going to be a unitless quantity. Okay, because v2 is already a voltage, so there is no need of multiplying anything else to make it a voltage, because this is already a voltage. Okay, now this I1 is a current. Okay, and we know that when we multiply current with a resistance, it becomes a voltage. Okay, so in that sense we can say that h11 will be having a you will be having a unit of the resistance, so that the resistance multiplied by the current becomes a voltage. Okay, and the condition is satisfied, the required condition is satisfied, that the LHS unit should be equal to RHS units. Okay, so h11 is basically, and this you can find in another way, that if you make v2 0, means if you short circuit the output side, v2 becomes 0, and this whole term disappears. Okay, and you are left with only h11 I1 equal to v1. So h11 can be calculated as v1 by I1, given the condition that v2 is equal to 0. So from that sense we can define h11 is v1 by I1, that is the input impedance, given that the output side is shorted. Okay, so from there also it is coming as a unit of impedance. Okay, now here, look at here, the second equation, this I2 is the current, so this term should be having a unit of ampere, this term should also be having a unit of ampere, right? This is I1, already a current, so we don't need any extra unit. So H21 becomes the unitless quantity. Okay, and V2 is voltage. Okay, and H22. So H22 becomes a conductance. So when you multiply the conductance with the voltage, it becomes a unit of current. Okay, and also when V2 is 0, okay, H21 becomes I2 by I1, given that V2 is 0. So H21 is I2 by I1, that is output current by input current, that is forward current gain, given that output is shorted, right? And similarly, when we assume that I1 is 0, that is input current is 0, means input side is open circuited. Okay, I1 is 0 means input side is open circuited. Then this term becomes 0, and then we can find the equation for H12. H12 becomes V1 by V2. So voltage by voltage, a unitless ratio. So actually this is V1 by V2 means input voltage by output voltage. So it becomes a reverse voltage gain. Reverse voltage gain. Reverse voltage gain means, reverse means why? Because this is a ratio of input by output. Okay, if it had been a ratio of output by input something, we would have called it a forward ratio. But here this is a ratio of input voltage by output voltage. So we call this as a reverse voltage gain. Okay, and given that the input side is open circuited, I1 is 0. Okay, now similarly in this equation also, if I1 is 0, this term becomes 0, and H22 becomes I2 by V2. I2 by V2 is again what? This is a conductance. We had already seen this. Okay, so this becomes output current by input current. It means that it is output conductance, given that input current is 0 or input side is open circuited. Okay, so this is how we can identify, we can uh, know the characteristic of these four parameters: H11, H12, H21, and H22. Okay, now these four parameters are called as hybrid parameters: H11, H12, H21, H22. Okay, where V1 is the input voltage, V2 is the output voltage, I1 is input current, I2 is output current. Okay. And these are the equations that are hybrid parameter equations for a common emitter BJT. Okay. So how do we recognize that this is a common emitter? This is for a common emitter BJT. Look at these, the second subscript. The second subscript, this is HIE. E means E is for common emitter. HRE. E is for common emitter. Okay. E, then HOE. Okay. Now this H11 is called as HIE here. H12 is called as HRE. H21 is called as HFE, and H22 is called as HOE. So let us see what is the significance of these symbols, these subscript I, R, F, and O. Okay. HIE basically is the input impedance. Okay. Look at here. We knew that H11 is the ratio of V1 by I1. So this is having a unit of impedance. Okay. And since this is the ratio of V1 by I1, so V1 is input voltage, I1 is input current, so this becomes the input impedance, input side impedance. So that's why this is given with the subscript of I. Okay. And in the case of common emitter BJT, VBE is the input voltage, if you can recall. Okay. And IB is the input current, base current. Okay, and this is the V2, VCE, the collector emitter voltage is the output voltage, and the collector current is the output current. Okay, and you can compare these two equations. Compare. Okay, now HRE. HRE is the reverse voltage ratio. Reverse, again as I told that reverse voltage ratio means it is the ratio of input voltage by output voltage. Okay, and because of this, in this sense, this R has been inserted here. HRE, the reverse. Okay, HFE. F is for forward, and what forward? Actually, forward current transfer ratio. Forward current transfer ratio or forward current gain. Why? because HFE is the ratio of IC by IB. This is IC, this is IB. IC is the output current, IB is the input current. So output by input means it's a forward current ratio or forward current gain. Okay. Now the last one is HOE. O for output admittance, because this is the ratio of output current IC by output voltage VCE. So current by voltage ratio is admittance, and this is output current by output voltage, so it's output admittance. Okay. So this is how you can understand. You might be knowing this already from your earlier subjects. Okay, just a quick review of these parameters, and we can use these equations for modeling the BJTs. Means we can replace that particular BJT component in any circuit with the circuit that results from these two equations. Okay, and then we can go for analyzing that circuit using our methods that we are aware of, like the superposition theorem or Norton's theorem or Thevenin's theorem or KCL, KVL, whatever thing is required. Because unless and until we convert this particular BJT in terms of resistors and current and voltage sources, dependent current and dependent voltage sources, we cannot analyze the circuit. Okay, so it needs to be converted into some sort of those electronic components, and then we can go for the analysis of the circuit. Okay, so these are hybrid parameters, and this table I have inserted here, that is showing the hybrid parameter for the uh, transistor 2N4400. So this is NPN transistor, and these are the four H parameters having typical values. For example, HIE, the input impedance, that is taken as taken at IC 1 milliampere, VC 10 voltage at a frequency of 1 kilohertz. Okay, for the transistor 2N4400, the minimum value would be around 0.5 kilo ohm, and the maximum value can go up to 7.5 kilo ohm. So this will lie between 0.5 to 7.5 kilo ohms. Okay, so now you decide what is the uh, is this low, is this a low value, is this a high value, or or is it a moderate value. Okay, now you can decide. So this will be in terms of some few kilo ohms, the input impedance for a common emitter BJT. Okay, now the reverse voltage gain, and since this is reverse, this is also called as feedback ratio or voltage feedback ratio. Some portion of output voltage is being fed to the input side, so this reverse thing. Okay, and this HRA is 0.1 into 10 into sorry 0.1 to 8, the maximum value, and into 10 to the power minus 4. Okay, so this is low value, very less value. Okay, and the HFE, the forward current gain, would be somewhere between 20 and 250. Okay, and this HFE, that is the forward current gain for the case of common emitter. We know that in the case of common emitter, the output current is collector current and input current is the base current, and the ratio of output current by input current, that is IC by IB, is the ratio is called as beta. Okay, so this HFE is actually also the value of beta. So beta would be somewhere between 20 and 250. Most commonly it will be around 100 and 150, around 100 or 150, somewhere near that value. For most of the cases you will find like this. Then the HOE, that is the output admittance. This will be somewhere some few micro Siemens. Okay, micro Siemens, in terms of 10 to the power minus 6 Siemens. Okay, So similarly, there are whenever you look at the data sheet of any particular transistor, any particular BJT, you will find these parameters given in that data sheet. These values are given so that you can compare the you can have an idea overall idea of the performance of BJT, and you can compare those BJTs with respect to other BJTs. Okay, in terms of H parameters. Now, let us come to the circuit, the Darlington pair. Okay, and see what these four parameters that are important for an amplifier. How are these given? Now, the derivation is not included in the text. They have given the expressions directly. Okay, the input impedance for this Darlington pair is given by this expression, that is Ri1 equals approximately equals to 1 plus HFE square into Re by 1 plus HOE dot HFE dot Re, where Re is that resistance that was inserted in the emitter branch, remember. Okay, Re. So this is the Re. Okay, get here. And these are the H parameters. HFE, the forward current gain. Okay, and HOE is the output admittance. And remember, the output admittance was in terms of 10 to the power minus 6, 10 to the power minus 6 Siemens. So it was in terms of 10 to the power minus 6. Okay, and so it means that this will be in terms of 10 to the power minus 6. This HOE, okay, and this HFE is the beta. It would be around 100, 150. So 100 means 10 to the power 2. So 10 to the power 2 into 10 to the power minus 6 would be 10 to the power minus 4. Okay, 10 to the power minus 4, and into Re. Re would be typically Re would be in what are the typical values of Re? So this term becomes 10 to the power minus 4. Okay, 10 to the power minus 4, and whatever Re value is there, that will be multiplied with 10 to the power minus 4, and depending on that, okay, either it becomes a significant value or it becomes a negligible value. Okay, so that will decide whether to keep this term or not with respect to 1 here. Okay, and if it becomes negligible here, hmm, very less than 1, then it simply becomes 1 here. Okay, and it becomes simply equals to 1 plus HFE whole square into Re. Okay, that will depend on the value of Re actually. Okay, so we assume that HFE1 is equal to HFE2 is equal to HFE, because this Darlington pair is using two transistors, Q1 and Q2, and they will be having their own hybrid parameters. So for the case of simplicity, let's assume that the hybrid parameters of Q1 and Q2 are equal, so that HFE is equal to HFE1 equals to HFE2, and let us say this is a common HFE value. Okay, and similarly other H parameters are assumed to be same for the two transistors. Okay, and this equation is particularly valid for this condition, HOE dot Re smaller than 0.1. Okay, this will come clear because this will become clear when you go through the derivation completely, when you go through the complete derivation. Okay, so basically you have to remember this equation, the equation for input resistance for this Darlington pair, and some simple questions may come based on this formula. Some value, the values will be given. You have to use this equation to solve for the input impedance or input resistance. Okay, for example, let us assume that HFE is 50, that is beta is taken as 50. Okay, HIE, the input impedance, is taken as around 1.1 kilo ohms, HOE output admittance is 24 into 10 to the minus 6 Siemens. Okay. Then for RE, look at this value. The RE 3 kilo ohms, some few kilo ohms. So this RE is some few kilo ohms generally. So for RE 3 kilo ohms, okay, this will give us a value of RI1, that is the input resistance at around 1.64 mega ohms. So now this mega ohms means a very high value. Mega means 10 to the power 6 ohms. So there was a point that the input impedance of this Darlington pair is very high, and this is also verified from this equation. Okay, from this example. Just a minute. Okay. The voltage gain. The voltage gain uh, is given by this equation 1 minus HIE by RI2. Okay, 1 minus HIE by RI2, and where RI2, HI is the H parameter, the input impedance parameter, and RI2 is the input resistance of the second stage. Okay, there are two stages. There are two transistors used here, so there are two stages, and this RI2 is the input impedance of the second stage. Okay, and this is given by this equation, that is RI2 is equal to 1
मेरे
plus.
से भी नहीं डर रही है
Hey Prachi,
और
Prachi,
दूँ ना उठा के समझ में आ जाएगा
Prachi, unmute
फिर
yourself.
डांटोगी 4-5 दिन नहीं आएगी
Someone please tell Prachi to unmute. Sorry, mute herself. Hey Prachi, hello. Hello. Prachi, are you listening? Hello. Prachi, I am speaking to you. Just respond here. Hello. Oh, look, this is the thing that I don't like about online class. Okay, you cannot. It is very difficult to talk with the students, and you cannot see what the students are doing, whether they are listening to your lecture or doing something else. It is very hard to monitor. Okay, students, I am asking in general, are you enjoying these online classes?
No, sir.
No. Why? Tell me the reason.
सर कॉलेज जा नहीं पा रहे सर
कॉलेज जा नहीं पा रहे हैं और घर में पढ़ने में मन नहीं लगता होगा. I know that. Okay, so this Ri2 is given as 1 plus HIFE Re. Okay, remember Re was the resistance that was there in the emitter terminal. HFE, what is this? This is the beta. Okay, so you can ignore 1 with respect to HFE, or you can keep it here, no issue. Okay. Okay, so HI E. What is the time now? 11:05. Do you have a class after this?
नो सर
No, sir.
Okay, right. Okay, so generally the value of this HI will be less as compared to RI2. Okay, and Look at here, because this Ri2 is the multiplication of Re. Re is some few kilo ohms, and HFE, the beta would be around 100, 150 something. So 10 to power 2 into 10 to power 3 becomes around 10 to power 5. Okay, so in the denominator it becomes around 10 to power 5, and input impedance would be some value, but usually very less as compared to 10 to power 5. Okay, so in that by that logic we can say that generally AV, the voltage gain would be a value that is close to unity. Okay, that is very close to 1. Okay, so like that. The current gain. The current gain AI is given by this equation, 1 plus HFE whole square by 1 plus HOE dot HFE dot RE. Okay. Now you can go on analyzing this particular term. Okay. What would be the value, typical value of AI in this case? Okay. Will it be a high value or will it be a low value? You can go on analyzing this term, this equation. And we know that from the diagram, we know that the output is taken across the collector branch, okay, sorry, the emitter branch, and the input is fed from the base branch. Okay, so output is the emitter current and input is the base current, and emitter current is generally very high as compared to base current. We know that thing. Okay, so the current gain has to be high. So can we justify that thing here? Okay, look at here, 1 plus HFE. HFE is beta, generally 100 or 150 or 200. Okay, so 100 square becomes 10 to power 4. Okay, now in the denominator we are having 1 plus HOE. HOE is HO, output admittance. Output admittance was generally in terms of 10 to power minus 6. Okay, in multiples of 10 to power minus 6. HFE, let's say 10 to power 2. So 10 to power minus 6 into 10 to power 2 means 10 to power minus 4. Okay, and this RE, let's say some few kilo ohms. So 10 to power 3. So this becomes 10 to the power minus 6, 10 to the power minus 4 into 10 to the power 3. That means 10 to the power minus 1. 1 by 10, 0.1. Okay. So 1 plus 0.1 is approximately 1. So the denominator is not affecting the overall term much. Okay. So this whole square will come out to be a high value. Okay. So in that sense we can, this is, we can get a general idea of that what would be the values of these four important parameters of this amplifier. Okay, although it will not give us a very accurate, but it will give us a general common idea that AV will be around 1, AI would be a high value. So whenever you solve a problem and you get a low value of AI, then you can go and introspecting that particular solution. Why I'm getting a low value? Have I done some mistake or what? Okay. Then output resistance is given by this equation. R naught is equal to uh, R naught is equal to, what is this? Let me check in the book. This is RS, sorry. RS plus HIE by 1 plus HFE whole square plus HFE by 1 plus HFE. Okay. Now, can we analyze this? Can we have an idea about this? Okay. HFE is beta. Beta is generally high as compared to 1. Okay. So this whole term would be approximately equal to 1. Okay. And this RS, the source resistance of the input source. Okay, so RS plus HIE. This HIE is the input impedance. Okay, we already know that input impedance is quite high. Input impedance is quite high. This is divided by 1 plus HFE whole square. HFE is beta. Beta is also high. Beta is around 150, 200, whatever. So this will be 100 square means 10 to the power 4. Okay, so this would be, let's say if this is in mega ohms, 10 to the power 6. This becomes 10 to the power 4. Okay, so overall you will get around 10 to power 6 by 4 means 10 to power 2. So the output resistance would be some around a few hundreds of ohm. Okay, a few hundreds of ohm. Okay, so you have this rough idea. Okay, that output resistance would be in terms of some few hundreds. The input resistance is in terms of some few mega ohms. Okay, and the voltage gain is around unity, and the current gain is a high value. Okay, now you have this rough idea about this emitter follower, and then wherever you insert this in your circuit, then you can analyze that, you can understand that particular circuit uh, more closely. Okay, so I think yeah, there is a problem for you, a small problem, that compare these parameters, that is these four parameters, that is the current gain, voltage gain, input and output impedance. Okay, with that of a single stage emitter follower or single stage emitter amplifier. So this consisted of two stage. Now consider these values with the case of a single stage one. Okay, let's go through the some of the points, important points regarding this Darlington pair. Okay, the it has got a slow switching speed. The bandwidth is limited. It will not give you a very large bandwidth. The high overall base BE, that is base emitter voltage, that is 2 VBE, and this is clearly visible because we had a back-to-back connection of two transistors Q1 and Q2. Okay, and the Q1 base voltage input voltage was like VBE. Okay, and the Q2 was having VBE. So when you add VBE plus VB, it becomes the overall 2 VBE. And why is this important? Okay, because we need to bias the base emitter junction in forward bias. So unless you bias these junction in forward bias, you cannot use these as an amplifier. Okay, this is the thing, this is the fact. And here the requirement is that we need 2 into VBE, and knowing the fact that VBE for a silicon transistor is around 0.7 voltage, so we require at least 1.4 voltage at the input side. We require at least 1.4 voltage at the input side so that the amplifier works properly. So this is also a limitation. Okay, this is also a limitation. For this case, the saturation voltage is 0.7 volts. Okay, which can lead to power dissipation. It is having a high value of saturation voltage. Okay, generally we know that the saturation voltage is around 0.2 or 0.3 volts. Okay, generally, but it is high here in this case. And these are the points regarding this Darlington pair. Okay, so the next topic is cascade amplifier. Okay, students, we are having how many students here? 56. Okay, good number of students. Hmm. So should I continue this, or in the next class should I start this? What do you think, friends? I am asking you.
Sir, next class.
Pavani, next class. Yes, other students.
Next class, sir.
Okay, okay. I will take this in the next class. I will continue from here, the cascade amplifier. And in the meanwhile, I would like to ask that did you get the PDF copy of this book, Industrial and Power Electronics by J.K. Mithal and Manisha Gupta? Do you have the PDF soft copy?
No, sir.
No, sir.
No, no, because I think this is not available on online. I had searched a lot also. So what I will do is I will take the photos of the relevant chapter, then I will share it with you. Okay, and I will
Okay,
also
sir.
share these slides with you. So don't worry about that thing. Okay, because this book is particularly important for this for the portion that I will be covering, the module one and the half portion from module two. Okay, the first 1.5 module. Okay, okay, ठीक है चलो, we will continue in the next class and give your attendance here. Okay, give your write your name. So write your roll number and name. First write your roll number, then your name. All are from section B, I assume. Okay. So first write your roll number and then name.